Hello everyone, my name is Karam, and I'm defending the thesis titled The Objective Validation of Airport Terminal Architecture Using Agent-Based Simulations. This presentation will give a summary of each section of the thesis. I'll start with an introduction of the abstract and hypothesis, then I'll highlight some background context, concepts I'm using, and testing I performed. Finally, I'll conclude with key impacts for architecture and the overall takeaways. Beginning with a summary of the abstract. This thesis explores how airport terminal architecture is tested before it's built. The purpose of testing architecture is to make sure the layout of the terminal aligns with the rest of the airport systems. Airports are considered complex facilities that process tens of thousands of passengers every hour, handle logistics, and control security. These complexities can cause architects to rely on their intuition to judge how well a design aligns with other airport systems without formal testing. However, it is important to get a terminal right the first time, because it is difficult to make changes after it's built. Because of these complexities, testing airports typically involves using some form of computer simulation. Architects do currently use what are called crowd simulations to check passenger behavior in the built environment, which do actually do a good job of approximating people on a large scale. These tools are often used to check people in process flows and emergency evacuations. While these are important, the design of a terminal is often more than just flows and egress. As a result, these simulations do not consider how people use the architecture to make decisions. If a passenger hasn't seen the terminal before, they will be unaware of where to go or what to do. I'm sure some of you have also experienced trying to find your way through an airport. You don't necessarily follow a straight path to your gate. You may meander around and rely on what you can see around you to tell you where to go. Fundamentally, it's the surroundings, or the architecture, that is informing our decisions. However, these aspects are not typically addressed in these kinds of analysis. For this thesis, my intention is to use passengers to test architectural layouts. Imagine taking a bunch of people and dropping them into a simulated terminal, giving them a task to complete, such as boarding a flight. However, we're not going to tell them where to go. Instead, we're going to force them to use the building to make decisions by giving them perception of their surroundings. Now, whether or not they complete their tasks, their experience can quantify how well the terminal was arranged. Ideally, this can differentiate between different layouts as a probability of passenger interaction. To illustrate this, I have explored making a prototype simulation using commonly available software. The prototype builds on existing research from crowd simulations, statistics, and wayfinding, commonly used for egress. I'm incorporating human perception for a new architectural decision-making process, and I'm also attempting to quantify the aspects of architecture that may be important for a successful airport. These are concepts that already exist in other applications, but have not been combined in this way before for architecture. To explain how this is possible, I'll summarize the concept of airport design, validation, statistics, and simulation modeling. Starting with airport design. One reason I am looking at airports is because they have established research showing that simulations are one of the only ways to understand these complex systems. Airports use simulations for almost everything, including analyzing the airspace to ground operations. A basic airport terminal is divided into two areas, called the land side and the air side, which is separated by a security line. Every terminal includes core spaces for passenger processing and hard points that need to interface with other systems. The core areas typically include a check-in processor, security screening, immigrations, a gate concourse, hold room, and a baggage claim hall. But before starting the architectural design of the physical building, airports need to identify the capacity of the facility first. This is done using demand forecasting. This estimates the expected number of passengers during what is called the peak hour, or when the airport is at its busiest. The square footage of the terminal building can then be estimated based on the density of passengers using level of service factors. This gives a rough area per square foot based on some passenger comfort level. The size of the terminal can then be chosen as a balance between the economics of available space and these passenger comfort levels. Once a rough size of the airport is established, architects can begin designing and arranging spaces for the physical building. However, architects are required to design the terminal within the hard points established during planning, which are where the curb is, where the security line is, and where the plane gates are. These cannot change. The goal is to analyze the arrangement of these spaces between these hard points so that it's consistent with the planning stages. Validation and statistics. For any testing or design to provide us useful information, it must go through a verification and validation process. These are an established scientific practice that checks if a system or object is meeting requirements or expectations, and that the tools we are using are giving correct values. Any system can be analyzed using validation, as long as that system has some established purpose and a desired tolerance. Validation can be as informal as a design review, as seen in architecture, physical testing, as seen in material science, or formal mathematical logic, as seen in computer science. Perfect validation for a simulation is impossible to achieve due to the biases in the models we create and the uncertainty of recording real-world data. However, validation is most effective for increasing the confidence of the model's output, so designers can rely on it to communicate information. In other words, if a design can meet some sort of criteria, then that can be used as proof that the information will be representative of the real world. Because of the wide range of differences in human behavior, simulating these types of systems often requires using probability and statistics. This is because most things that are difficult to predict appear to occur randomly. A common simulation approach using probability is called the Monte Carlo method. This uses random samples to get a numerical result for a system that is difficult to solve analytically. It is easier for airports to consider a random sample of passengers than the entire population. Monte Carlo takes advantage of the law of large numbers, which states that any characteristic of the system will converge to a stable value given enough samples. The result of a Monte Carlo produces some type of probability distribution. This represents the sum of many independent events, which illustrates a range of behaviors that are likely to occur. Any random event in an airport can be quantified based on these distributions. Simulation modeling. There are different types of simulations depending on the application in an airport, but terminals commonly use discrete event simulations to model crowds, which updates passenger movement in small time steps instead of continuously. Passengers are commonly represented using intelligent agents. An agent is a simulated object that has the ability to make their own decision to achieve some goal. Agents are also able to interact with their surroundings based on some defined characteristics or behavior. But firstly, to understand what exists out there already, I initially reviewed 3 discrete event simulation software that are currently used in industry for terminal analysis. These were MassMotion, Arena, and FlexSim. MassMotion is primarily used in architecture for crowd flow, emergency evacuations, and wayfinding. It models people as agents and gives them passenger-like characteristics. MassMotion is more than capable of modeling architectural spaces. However, its main limitations are that its agents are already aware of their targets from the beginning, they cannot get lost, and their navigation is primarily influenced by the density of surrounding people. However, this is still useful for egress and evaluating LOS factors. Arena and FlexSim are both used in industrial applications, which are strong at modeling traffic flows, logistics, processing, and crowd flows. Both tools represent people as a flow item in a system, which means that they don't have self-agency. In Arena, the biggest limitation is that people follow a linear, predefined path to their targets and do not have spatial awareness. Likewise, FlexSim also provides its people the shortest path to their target without any influences from the surrounding environment. However, unlike Arena, FlexSim does use an A-star navigation, which can adapt to block paths and mimic people walking in open spaces. Despite these limitations, these tools are still important for airport analysis, doing an excellent job of modeling crowds and industrial processes. The main elements that are missing for architecture are the ability for people to be lost or wander around, and the lack of decision-making considering the built environment. This is mainly the result of agents being aware of their targets from the beginning. To address these issues, I took these ideas into a prototype simulation. This includes being unaware of your targets, getting lost, and using the built environment to make decisions. To understand how this works, I'll summarize the concepts of agent decision-making, perception, and valuation, starting by considering how decision-making and perception work together. Agents that don't have existing knowledge of a space must understand what to do based on their ability to read their surroundings. This can be represented by a cognitive decision-making process, which describes how to gain knowledge and interpret information. For the prototype, I'm using an established method called Sense, Plan, Act. This simplifies agent decision-making into a linear sequence, which can be easily coded into a computer. Agents first use sensors to read the environment, like using your eyes to see. Their mind then takes that information and interprets what to do. They can then act out their decisions using effectors, like legs or arms to move. This process repeats until the agent achieves their goal. Agent knowledge is based on the concept of affordances. These are properties of an object that have use for a person, whether for good or for bad. For example, an agent is looking for security in a terminal. They will not be told where the area is. Instead, they have knowledge of objects that are part of the screening process, like a metal detector. While searching the airport, agents are looking for objects like a metal detector or signs, cues, and other objects that they know will provide them that clearance. Agents make decisions based on what they perceive. For the prototype, this is simplified to the area that is visible within their field of view. If an agent sees an object that they recognize, then they can engage with that object. But if the object is invisible, then they can't perceive it. Agents store this type of information in their memory. This includes long-term memory of their assigned targets and characteristics, and short-term memory of their current behavioral state, the current spaces they're in, and local targets in their field of view. Long-term memory is not expected to change over time, whereas short-term memory will change. Architecture valuation. A hard part of this thesis was trying to figure out how to quantify architectural elements. It's not as simple as asking the value of a column or materials. Architecture is influenced by a range of factors like culture or economics, which may not have only one solution. However, I chose to focus on user interaction. The only issue is that people can value many different things in the built environment, which depends on their background. This can be solved by combining the values from multiple people. A common approach is the method of prioritization. This is a judgment analysis technique that allows us to compare a wide range of values relative to each other, one-to-one. Prioritization works by ranging subjective attributes on a scale from 1 to 9, which are compared in a matrix and normalized using eigenvectors. To narrow down what attributes are important to people in an airport, I use the concept of airport domains. These are features in a terminal that people care about the most, indicated by passenger experience surveys. These are organized into processing and non-processing domains, 6 of which I've selected to be related to architecture, 3 processing, check-in, security, gate availability, and 3 non-processing, waiting area comfort, availability of food, retail, and washrooms. To combine these domains with architecture, I've developed a scoring system that tries to calculate a value based on the level of interaction. This depends on several factors, including the purpose of the space, what people can perceive, what elements they interact with, and process time. In general, an architectural score for a given domain can be made up of any combination of these factors. To demonstrate how the prototype works, I'll walk through some testing I did, and this includes some validation, component testing, terminal layouts, and a real-world airport comparison. I chose to build the prototype using Unity, which is a game engine. Unity allowed me to code new agent behavior from scratch and animate crowd movement within custom architectural models. I was also able to build onto pre-made elements like A-star navigation and field of view geometry. Validation and component testing. The first set of tests involves the verification and validation. I used an existing standard for evacuation simulations by the IMO and NIST, which is also used by Mass Motion. This covers about 19 tests related to components, crowd behavior, and evacuation. For this thesis, I only selected 4 tests that were relevant for basic agent behavior. These are corridor walking speeds, rounding corners, flow rates, and assigned demographics. To demonstrate one of them, I'll show rounding corners. The goal of this test was to show that agents don't walk through walls. 20 agents start from one side, and their goal is to walk to the door on the other. Although they do bounce around a bit, you can see they successfully navigate around this corner without cutting straight across the door or clipping through the environment. This test wasn't concerned if people walk through each other, only the walls. Out of the 4 tests, I was only able to validate 3 of them, except for exit flow rates. This was caused by agent proximity issues, where people kept clumping together, causing the flow rate to spike higher than what was allowed. To avoid these issues for later tests, I just limited the number of agents I simulated. Next is component testing, which explores the new features that I proposed in this thesis, including perceptive wayfinding, field of view, visibility, and priorities. For this presentation, I'll just be demonstrating wayfinding and priorities. The first test is wayfinding. This layout is designed to illustrate the difference between direct navigation, which is used in FlexSim, and perception navigation. There is an entrance on one side and 2 gates, A and B, on the other. In the middle, there's a T-junction with a shorter path to the left and a longer one to the right with a switchback. In the middle of the junction is a wayfinding sign that says A is left and B is right. Agents enter this layout with the task of getting to gate B. When an agent enters the simulation, using direct navigation, a path is generated from the entrance all the way to gate B. As you can see, the path takes the shorter path to the left, or in other words, the lowest cost path. It also goes around this orange restricted area, which gives a higher navigation cost. The agent then follows this path exactly without any influence from the wayfinding sign in the middle. Now, if the agent is given perceptive navigation, you can see that when the agent enters the simulation, a path is not generated all the way to gate B. Instead, it is limited to their field of view, which is represented by this light area. And since the wayfinding sign is only visible information, the agent walks up to read it. And at this point, you can see in this image shows what the agent can see at the junction. From this perspective, the view to gate B is completely blocked by the walls, and the agent can only see the wayfinding sign. Now back to the simulation. If I continue this, once the agent reads the sign, they take the path to the right, following the sign to gate B. And as you can see, the agent follows the corridor down the switchback. And although this may not be representative of how everyone might behave at a junction like this shows that if the agent is only reliant on the information they perceive, then the environment has the potential to influence them to take a completely different path, even if it's not optimal. Eventually, when they do reach the end of the corridor, gate B becomes visible, so they walk directly towards it. The next test explores if agents can follow different behavior if they're assigned different priorities. This layout is designed as a simple departure concourse. The blue area represents an entrance corridor to a much longer terminal. The green area represents a single gate hold room, and the purple area represents linear food and retail areas. When a passenger enters this concourse, their flight is not ready for departure, so they have a choice. They can either wait in the hold room or go to the retail area. Agents are randomly assigned a food priority on a scale of 1 to 9. Those with a priority of 5 or higher are expected to look for food, whereas those with a lower priority just wait in the hold room. Agents are colored based on their current mental state. Light green agents are looking for food, red agents are waiting, yellow agents are queuing, and orange agents are processing at the counters. Once agents have gotten food, they can come back to the hold room to wait. After a given time, the flight will be ready for boarding. Agents then turn dark green, and they all walk directly to the gate, who all happen to be aware of departure at the same time. Although this is a simple test, it is meant to show that people who might value different things in the same space can simulate different behavior. Terminal layout testing. This explores the layout of a basic departure terminal. The intention was to replicate different iterations that an architect might consider. Each layout has the same hardpoints and core spaces, and I'm testing if the security area was aligned to 3 different locations, that being in the center, asymmetrically to one side, and rotated perpendicularly. The idea is if all else is equal, then the difference in value should represent the differences in the floor plan. To illustrate what happens, we're going to follow a typical passenger in the centered layout. Entering the terminal, agents are looking for the check-in area colored in blue. The check-in process is simplified, with agents walking directly to the first counter they see, turning orange once they start processing. Once complete, their bag is dropped off and they begin looking for the security area. This agent notices the security queue after reaching the end of this wall, causing them to become purple. Agents then turn yellow when they enter the security line. I have not modeled the queuing process like a proper simulation. However, I have applied a time delay factor, which does account for a random queue time. At the end of the line, the agent selects an available aisle for screening. Once processed, the agent walks through the metal detector, indicating that they've been cleared. The agent then follows a wayfinding sign to the left, since they're departing from gate A. Like the other test, their flight is not ready for boarding right away, so this agent then goes to get something to eat based on their food priority. Once completed, the agent walks back around to the seating area to wait until the gate opens for boarding. This test was run using hundreds of passengers to get an average score for the layouts. This was also repeated for the asymmetrical layouts, and it was repeated for the perpendicular layouts, which gives a good sample of information to compare against. The asymmetrical layout affected how passengers access security. If agents checked in on the far side of the terminal, then they were more likely to wander around, illustrated by the light blue agents. Although if passengers checked in on the same side as security, they had a much easier process since they could see the area sooner. In the perpendicular layout, the security area is surrounded by walls, which can only be entered from one side. As a result, passengers who checked in on the right could not see where the security area was without walking to the other side. As shown here, the agent's perspective had no view into security, which might benefit from some kind of signage. So, after testing hundreds of passengers, their scores can be used to create a probability distribution of values based on interaction and priority fulfillment. As you can see, distributions are actually quite similar, averaging roughly around the mid-70s. Although the center layout in blue did have a slightly better distribution, followed closely by the asymmetrical in orange, and then perpendicular in pink. For those tests, passengers were assigned random priorities, which means that each domain was given a random value from 1 to 9. But how would the scores have changed if passengers were given different priorities? So I reran these tests using passengers with only high security priority. The idea is if the security was modified, then it would impact the passengers the most as an extreme case. And this graph shows the high security priorities did give distributions that are more spread out than the random priorities. It shows that the center layout does have a higher score on average compared to the other two, likely due to the better visibility. The values here are much lower than the random test, since security is practically the only domain passengers are judging the airport with. Airport comparison tests. This test explores if the prototype simulation can predict the value for a real airport. The goal is to compare a known airport with high passenger ranking against one with low ranking. I've selected Singapore Changi and Toronto Pearson, which are the higher and lower ranked airports respectively, based on these passenger experience surveys. Since architectural value is based on passenger interaction, Changi should score better than Pearson. To simplify the scope, the design only considers essential check-in and security areas for international departure, which are highlighted here for both Singapore on top and Toronto on the bottom. I've assumed passenger priorities are randomly assigned using the same 6 domains, and the simulation ends before passengers reach the pier gates and hold room. Here is a time-lapse of Singapore Changi. Terminal 1 is a symmetrical check-in processor with a Y-shaped centralized security area. Security opens out into a retail court at the back, and the access to the gates extends to the far right and left of the court. Here's another view of Changi from the top, showing the transition between the check-in to security. And this is a closer view of the check-in area. And here is a view of security. Now, I don't know exactly how the security aisles are laid out here, but I do know that the security opens out into this retail court space directly. Now, here's a time-lapse of Toronto. Pearson Terminal 1 is a segment of an arced processor building. International departure for non-US flights occupies 3 check-in aisles in the middle. The security is currently located perpendicularly to the check-in aisles on the left, and there's a food court and retail spaces along the outer radius of the processor. Here is a closer view of the check-in area, and here is a view of the security screening area. This leads to a narrow corridor in the back, which passengers take to the pier gates. And just like the other layouts, after testing with hundreds of agents, it produces a probability distribution of values. This is a histogram of passenger scores in Changi, which ranges between 60 and 90 and is most concentrated around 80%. And here is a histogram for scores in Pearson. As you can see, the values have a much greater variance, ranging as low as 30 and as high as 80 for someone, although the average tends to concentrate around 40%. If I extend the average scores out for 1,000 trials, this produces a distribution of expected values for each airport. And as you can see, Changi in blue is more concentrated around the mid-80s, whereas Pearson in orange has a slightly higher variance around the mid-40s. Given the conditions I've tested, this is the most likely range of scores we would expect to see for each airport. As a result, you could say that this confirms Changi has a higher value than Pearson on average. However, I believe it's not that conclusive. This chart breaks down the average scores for each airport terminal. As you can see, Changi in blue has a slightly higher values than Pearson in orange for the check-in and exit to the gates. This may be due to passengers in Pearson walking through the narrow corridor. However, Pearson does have a slight advantage for security, which may be caused by passengers in Changi having to walk a lot further than Pearson. But clearly this is not as big of an impact as it was for the non-processing domains of food, retail, and washrooms. As you can see, practically every passenger in Changi was able to perceive the non-processing domains, whereas in Pearson only a fraction of passengers were able to perceive the same spaces. Looking back at the floor plans, you can see that the amenity spaces in Pearson are behind the check-in areas in green, whereas in Changi, the security opens directly into these amenity spaces, which would be hard to miss. If in Pearson, if passengers didn't wander to the back, then they would have gone through security without noticing any retail or washrooms. This is likely a reason why passengers had a poor experience if they prioritized these aspects. However, I believe if I used completely different domains, this would have produced widely different values. To conclude the thesis, I'll discuss the results and findings, impacts for architecture and future research, starting with the findings and ideal simulations. A result of this thesis was creating a working agent simulation that can test some architectural layouts. Airport terminal designs could be quantified based on agent interactions after giving agents perception of their surroundings so that they could use it to make decisions. This type of simulation could also begin to approximate real-world airports relatively, using priorities to compare probability distributions. Although this prototype has achieved some success, it is far from ideal. But there are some attributes that I found would be beneficial for any architectural tool. This includes fundamentals of crowd modeling, incorporating perceptive decision-making, and using statistics to analyze architectural values. At a minimum, crowd modeling would address flow dynamics, social behaviors, and egress. Perception can focus on using people's perspectives for navigation to model behavior other than the most optimal one. And statistical modeling can help quantify uncertain conditions by estimating a range of behaviors. And this may not be involving prioritization, but could use other weight-based analysis techniques. And if generalized enough, agent simulations could be used to test any building type, including in addition to transportation facilities. For example, hospital designs may use agents to test patient interactions in waiting rooms or clinics. This could incorporate hospital domains to check how well patients complete checkups, wayfinding, or operations. Risks and impacts. Simulations can impact architecture by giving design iterations quantifiable values. Design choices that may seem intuitive can instead be backed up by results from testing. This is also effective for communicating design issues which clients might not be aware of. Simulations can illustrate behavior that designers may not have expected. For example, after seeing the Toronto Pearson test, airport planners may realize that the retail area was not the best utilized by international passengers. As a result, they may reconsider arranging the retail spaces to improve passenger experience or even business. This can also identify during the design phase or communicated during client meetings. Testing can also result in terminal buildings becoming more intuitive for people to walk through, minimizing how often people become lost or confused. Testing ensures physical spaces in the building have the right elements for people to become aware of what to do, like proper signage or placing washrooms in an area where people will use it the most or have the most likely to use it. For this to be effective, there needs to be data about passenger types and their priorities, which determines how agents will behave in the simulation. This can vary significantly based on different cultural backgrounds. For example, I have tested Toronto and Singapore, but a more thorough study should be considering the cultural differences between North Americans and Asian customs, which can result in completely different priorities or behavior. The risk of only relying on simulations is designing something that negatively affects people in the future. For example, airports used to have smoking lounges, but these areas were eventually removed in Canada once people became aware of the safety and health risks of smoking in buildings. Optimizing for a certain behavior like that today may not be representative of people's mentality in the future. Likewise, there is a risk of favoring certain communities of people over others, optimizing a terminal for a single demographic which may not represent a diverse population can cause minority communities to become segregated within the built environment. This may include people with disabilities or people with different backgrounds. Computer models are also good. Computer models are only as good as the information we provide them. The way simulations interpret information is going to be based on the designer's biases. The risk of blindly relying on these simulations is that they won't always be accurate. If a designer is not familiar with the context, then they risk believing the simulation as the only truth, without further critical analysis of the results. We cannot eliminate these biases, but only try to minimize our lack of knowledge and continually reevaluate our understanding of the world over time. We cannot predict the future with certainty, like psychohistory and Asimov's Foundation series, but we can continue to update our models as our understanding of social behaviors change. Future work. There are two directions that this thesis might be taken. One direction is automating the agent simulations, including exploring machine learning techniques to optimize for certain architectural conditions or passenger priorities. For example, I imagine a simulation where we only need to define the hard points, and we could let the simulation run thousands of iterations, updating the architecture until it reaches an optimal solution for the passengers. The second direction is to study how human behavior relates to architectural conditions. It's not simply testing how a wooden wall might affect people's behavior against a concrete wall. It depends on the context. For example, passengers may use a solid wall as a place to wait in a railway station, but that same wall may also be an obstruction for passengers looking for their platform. A good study would be conducting experiments with real people in existing buildings and recording how they interact with them. In conclusion, the thesis has demonstrated that architectural designs can be approached quantitatively. Ultimately, the most effective use of simulations is for clarifying uncertainty in the existing design process. This will not replace the role of the architect, it will only change how they think about design choices. Continuing to learn from these established practices will provide more scientific rigor for architecture in the future.